All right, so we're going to talk about using those plasmids we just talked about. So transforming bacteria or transformation of bacteria is how we put bacteria or plasmids into bacteria. We're not going to depend on conjugation. And really, if I want to have bacteria that can do conjugation, I really can't control how the plasmids are inserted and where they end up, right? So transformation is kind of the best way to go. Transfection or transduction, probably not as good of an option, just for the fact that, again, it's a little bit out of our control. If I'm creating viruses that are adding DNA to bacteria, then I lose some level of control as far as it being a cloning vector or an expression vector, or even how many are being transformed and when they're being transformed. So we're going to do transformation. That's going to be our method of choice. So remember, it occurs when bacteria incorporate foreign DNA into their cell from the environment. So we'll create an environment and we'll give it plasmids and we'll stress it so we increase the uptake of those plasmids. Okay, so a couple things that we can do to increase our chances. And the first thing is electroporation. So electroporation is the process of making bacteria what we call competent, right? So it makes the bacteria what we call chemically competent. I lost my pen again. So it makes them chemically competent. So we have a couple ways. We can use actual electricity, or we can use calcium chloride. So calcium chloride, when we put it in water, it separates into positive calcium ions and negative chloride ions. So if we have a non-competent E. coli cell, if you look at it up here, I have a non-competent cell, right? So what I have here, right? So the outside of the plasma membrane of this cell is naturally kind of negative of charge, and the plasmid is overall negative charge too because it's DNA and DNA is negative. So to try to get that plasmid to transfer into my cell membrane is probably not going to work very efficiently, right? So it's probably not going to be very efficient. Right? When I add calcium chloride to it, right? So the calcium chloride, this is really bothering me. Right. So if I add calcium chloride, what it does is it makes the cell competent by introducing pores or holes. Right. So when I add calcium chloride, now the calcium ions are taking some of the negative, they're attaching to some of the negative sites on those plasma membranes. And what they'll do is they'll create an open space, essentially a channel, where that plasmid can then enter in. So it creates these channels or pores for plasmids to enter in. And then when I have those pores at that point, my bacteria is what we call chemically competent, or it has the ability to take in plasmid. All right, so now that we talked about how to make cells competent, let's talk about the transformation procedure. Right? So the first thing we have to do, we want to start with a fresh culture of E. coli. Right? And we want to harvest it in the logarithmic phase. So if we look at these graphs on the right, these are the growth phases of bacteria. So remember that E. coli especially, lost my pen again, shucks. So E. coli Oops. So E. coli replicates every 20 minutes. So in 20 minutes, I go from 1 to 2, and in 20 minutes, I have 4. And then 20 minutes later, I have 8, right? And then I have 16, then I have 32, then I have 6. So it's exponential growth, right? So the first up to 4 hours is called the lag phase, right? So if you look at the graph, about the first up to 4 hours is called the lag phase, and that's right here, right? It's a slow growth because E. coli are just gathering resources. But if you look at between hours 4 and, let's say, 12, right? So if I come down to here, right? So 4 and 11 hours, right? Between this, right? This is my log phase, right? And then I have exponential growth. And I want to get my bacteria in that log phase because in my log phase right here, right, I have maximum replication. I have bacteria that are healthy and they're just reproducing, right? And they're the ones that I can get to create plasmids. Remember, if I'm going to make a cloning vector, I want to make a whole bunch of copies. So when I get in my lag phase, right? Stationary phase is next, right? So when I'm stationary, right, what we can say is my numbers aren't increasing or decreasing, so replication is equal to death, right? So it's still okay. So up to about 16 hours here, right? Up to about 16 hours here, I'm in a stationary. So really between 4 and 11 hours is best, but if I can get it before 16 hours, it's better, right? 18 hours. So the bacteria we use say that use before 18 hours, because at 18 hours, then I'm really in that death phase, right? At the death phase, I'm past the stationary phase, and death is greater than replication, so my transformation efficiency is much worse, right? Which is a problem when we work in schools, because we'll start our culture, and 24 hours later, we're going to come and do our transformation. Transformation still works, but it would work a whole lot better if we could, start it at night and come back the next morning and do it. Right? That would be much better. But we don't really have that option, right? And you can see, so this first graph on the top is what's predicted, and on the bottom, it's what's experimental, and you can see that it follows pretty closely, right? And they're looking at the optical density with a spectrophotometer. So it's about the same, right? It's about the same. Right, so transformation steps. So here's what we're going to do, right? First, we're going to get our E. coli, right? And we're going to expose them to calcium chloride. So our E. coli that we harvest in the log phase, we're going to expose them to calcium chloride, and we're going to stress them in ice water. So I'm going to get my calcium chloride, right? So my calcium chloride here is going to make cells competent. Right, it's going to make my cells competent and create pores, right? But then I'm going to put them in ice water, and I'm going to put it in ice water because what I want to do is hold those pores shut, right? It'll decrease the amount of growth I have right now because I'm in a log phase. I want to just stay in that log phase. So I'm going to decrease the metabolism, but I'm going to hold the pores shut until I'm ready to give it plasmids, right? So the next thing I'm going to do is I'm going to add plasmids to the mix, right? So I'm going to add plasmids to the mix, right? My plasmids are going to have an AMPR or a BLA gene, right? That's our antibiotic resistant, and a marker like GFP, which is like GFP is green fluorescent protein. Right, so I got my green fluorescent protein marker, And that's hidden, remember, in my bad operon, right? And I'm going to put that on ice for 15 minutes. So I'm going to cold stress it here, right? Then I'm going to take it and I'm going to heat shock it. So now I want the heat shock, I'm going to put it at 42 degrees Celsius for 50 seconds. Now, the temperature range for E. coli is 30 Celsius up to about 40 Celsius, right? And then the sweet spot for E. coli is 37 degrees Celsius. So after 40, they start to die, and below 30, they just stop replicating. Okay, but 37 is kind of the sweet spot for them. So I'm going to put them in 42, so I should be killing them, right? So it's not enough to kill them right away, but it's enough to stress them out where they're going to start looking for plasmids. So that 42 is going to open up the pores, right? I want to make sure I get my timing right, because if I leave them for a minute and a half, 2 minutes, 3 minutes, then I've just killed all my bacteria. But it's going to open up the pores and it's going to suck in those plasmids. I'm going to take those immediately off after it. I'm going to put it back in ice bath for 2 minutes. I'm going to close those pores again. I'm going to decrease metabolism, right? And I'm going to hold those in. And then I'm going to recover. So I've done all this stressing of my bacteria. And now I'm going to give them LB broth. Remember, it has all the nutrients in it. And I'm going to allow them to sit in that LB broth for 10 minutes, right? And slowly increase the metabolic rate, right? They're going to get their plasmids in there. They're going to start replicating again. And then I'm going to put them on plates and incubate. Right? So I'm going to put them on plates and incubate at 37 degrees overnight. Right? So I'm going to have 3 different types of plates. I'm going to have an AMP negative plate, so a plate with just LB agar, right? And I'm just going to check to make sure that I have living bacteria, right? I just want to make sure I didn't kill them all during the heat shock. I'm going to put them in ampicillin positive plates, right? So the ampicillin positive plate should kill all the bacteria except for my transformed bacteria. I'm going to put them in ampicillin positive and arabinose plates, right? I'm not giving them glucose at this point, but I'm giving them arabinose because I have a PR bad operon. So it's activated by arabinose, not lactose, right? So I'm going to check for recombinant DNA. So if I had plasmids without recombinant DNA, they'll grow on my AMP positive plate. If I have my recombinant DNA, right, then my AMP-ARA will be in there, my PBAD will be in there, and then they'll glow green, right? So they'll express my GFP. Right, so here's how we verify, or how we do the selection of transformation, right? So we can use a GFP or a GRP fluorescent markers, a green protein or a red protein, right? We have different strategies. There's a PUC18, which has a LAC-Z gene, so it grows blue on galactose medium. So I can do differential chromogenic medium like that. Additionally, right, I can put an MCS site in the middle, right, of the LAC-Z gene. So if I put my gene that I want in there, then it won't grow blue. It'll grow white. So there's different ways I can do it. So this would be an example. This is what we know as a knockout. So a knockout is where my insertion turns off a gene, right? Disables a gene, right? So I can use a knockout chromogenic. My antibiotic resistance genes, right, are added to all cloning vectors, and they help me verify. Right? Or I can add lethal genes, right? Genes that when I insert it, it kills the bacteria, right? So those are another type of knockout gene, All right. So one of the things we'll do is we'll look at transformation efficiency. All right. So my transformation efficiency is measured in CFU, and a CFU is a colony forming unit. Remember we talked about that before. Right. So if you look at this plate over here, right? So each of those green dots represents one CFU. It started with one bacteria and made thousands, right? So each one started from one colony forming unit, right? So efficiency, right? So we do it CFUs per microgram, right? So we calculate the efficiency based on the amount of plasmids we put in there. So for instance, if 10 nanograms of plasmid DNA is put into 500 microliters, and then we take 10 microliters and spread it onto our agar plate. So our DNA in micrograms will be the volume spread, right, times my DNA weight in nanograms, right? So that would be 10 microliters times the 0.05 micrograms, because this is in nanograms, right? And we'll divide that by my total transformation volume. Right? So if we do that, we get some sort of number here. Now I'm going to give you a worksheet to show you how to do this with a real scenario. Okay, so stay tuned for this. It's an oversimplified methodology of it. And it's really messing up here. Okay, now the other thing is, if you had to count all those dots, there's a couple different strategies. You can quadrant your plate. So this is called quadranting. So I'll draw a black line on the bottom, and then I can just count the dots in one quadrant and multiply it by 4. That's easier. You can do grid lines, equal grid lines. You can do a grid, then multiply it by the number of grids. Or you can use a colony counting app on your phone, which we have now, and you'll take a picture and it will count all the dots for you. Right? That's the way I prefer to do it. Use technology. All right, so other ways that we transform things, eukaryotic cells, right? We can do electroporation with electricity, right? But the plasmids we insert here for eukaryotic organisms are called shuttles, right? So shuttle essentially, a shuttle is a eukaryotic insertion vector, right? It'll have all the same things, right? But usually I insert my shuttle by transfection, right? So transfection is my method of choice. I can use it using a lipid membrane or a vesicle, right? Or oftentimes we do transfection with an engineered virus, right? CMV cytomegalovirus is a human virus that affects many different, it's a promiscuous virus. It affects many different types of cells, right? So it's ideal for using this, right? So just know that we use shuttle plasmids and we insert them via transfection, right? So another kind of interesting tool we have is we can insert via Biolistics. So Biolistics uses a gun. Right, so ballistics is the study of how bullets travel. So biolistics, kind of cool. I wish I could play with one of these at one point. So it uses a DNA-coated gold or tungsten. Tungsten is a very dense metal, right? Fragment, right? And these are microfragments, really small, to deliver DNA through the cell wall of a plant. So essentially, if you look at this bottom picture here, they just point the gun at the plants and they just spray the plants with DNA pellets, hoping that some of them land in cells and start to be reproduced, right? So you can attempt to make GMO products using biolistics. For the most part, they do it by transfection, right? So if you think about like BT corn. Right, so that's the most common GMO corn. The BT stands for Bacillus thermogenes, which is a type of bacteria. So you use bacteria to transfect, right? That bacteria makes a kind of a viral insertion RNA product, right, to insert it into the DNA of plants. Okay? All right, well, that's it for this time, and I will talk to you soon.